Hello, calculus fans. Let's talk now about linear approximations. So in the previous example, we wrote down an equation of a tangent plane, and it looked like this. Z plus 2 equals 4 times x minus 1 minus 4 times y minus 2. And if we just move things around and combine them all, we get z equals 4x minus 4y plus 2. Now, this linear function, 4x minus 4y plus 2, is a good approximation to f of x near the point 1, 2. The function L is called the linearization of f at the point 1, 2, and the approximation f of x being approximately equal to 4x minus 4y plus 2, this is called the linear approximation or the tangent plane approximation of f at the point 1, 2. In Calculus 1, we would have called this a tangent line approximation. For example, at the point 1.1, 1.95, the linear approximation gives f of 1.1, 1.95 is approximately equal to, and now we plug in 1.1 and 1.95 into the linear approximation, and we end up with negative 1.4. Notice that this is an approximation. And this approximation is pretty close to the true value of f of 1.1, 1.95. That ends up being negative 1.3825. So the whole point here is that these two numbers are very close. The negative 1.3825 is the true value of the function, and the negative 1.4 is the estimated value that we get using the tangent plane approximation. Now, tangent plane approximations, or linear approximations, only work if we choose points that are close to the point of tangency. So let's say we choose a point very far away from 1, 2. Let's say we go all the way out to 3, 6. That's pretty far away from 1, 2. Our approximation will not be quite as good. In fact, L of 3, 6 is equal to negative 10, whereas f of 3, 6 is actually equal to negative 18. So instead of being off by, somewhere in the second decimal point, this is off by a distance of 8, which is a lot. So, in general, we could say something like this, that an equation of a tangent plane to the graph of a function of two variables looks like this. Z is equal to f of AB plus fx of AB times x minus a plus fy of AB times y minus b. So this is just the general form of an equation of a tangent plane with the f of AB moved over. Then we can call this a linear function, and that's the graph of the tangent plane. Same thing, but we're calling it L of xy. This is called the linearization of f at the point AB. Then the approximation, where we say f of xy is approximately equal to the linearization, that's called the linear approximation or the tangent plane approximation of f at the point AB. Now there's a precise definition for what it means for a function of two variables to be differentiable. It's not enough just for the partial derivatives to exist. There's a more technical description. And essentially what it says is that a differentiable function is one where the linear approximation is a good approximation when xy is near AB. Another way of phrasing that is to say that the tangent plane approximates the graph of f near the point of tangency. It's actually really difficult to check the differentiability of a function using the definition. And I'm not actually going to give you the definition here because we're not going to work with that. But I can give you a theorem that provides a very nice sufficient condition for differentiability. And it just says that if you have continuous partial derivatives near AB, then the function f will be differentiable at AB. Okay, that's all for now.